Assalamu alaikum students. Today we will be dealing with the chapter magnetic effects of electric current. So this is another effect of electric current. Okay. In previous chapter, that is electricity, we have discussed about an effect of electric current. That was nothing but heating. Okay. So heating is an effect of electric current. Okay. So in the similar way, magnetic effect is also an effect of electric current. Okay. Let us first learn about the definition. The magnetic field is the region around a magnetic material in which the force of magnetism acts. Okay. So if this is a magnet, okay, if this is a magnet or if this is a current carrying conductor, what happens is the region around this magnet, okay, so this region around the magnet, this is nothing but the magnetic field. Okay. So the magnetic field is the region around a magnetic material. So magnetic field is nothing but the region around a magnetic material in which the force of magnetism acts. Okay. So whenever you are taking a needle or any other magnet near this field, what happens is it shows the force of magnetism. Okay. So magnetic field has both direction and magnitude. The magnetic field, it has both direction and magnitude. Direction is nothing but it has a particular direction in which it flows, and magnitude is nothing but it has some value. Okay. So the SI unit of magnetic field is Tesla. SI unit of magnetic field is Tesla. This is 1 mark question, 1 mark important question which you can say, what is the SI unit of magnetic field? So the SI unit of magnetic field is Tesla. Now a question appears, why does a compass needle gets deflected when brought near a bar magnet? Okay. So if this is a bar magnet and this is the needle, what happens if I take this needle near the bar magnet? It deflects. Okay. So what is the reason for the deflection of this needle? Okay. So the answer is due to magnetic field around the bar magnet. As I have said, if this is a magnet, this is the magnetic field, right? So in the same way, if I take this needle near the bar magnet, because of the magnetic field present near the bar magnet, what happens is it deflects. Okay. I hope you are clear with this question. The end of needle pointing towards north is called north seeking or north pole. Okay. As I said, if this is the needle, this is the north pole and this is the south pole. So this pole is called as north seeking pole or north pole. Okay. Next, the end of the needle pointing towards the south is called south seeking or south pole. So if this end of the needle is showing the direction near the south, so this is called as south seeking pole or south pole. Okay. Like poles repel each other and unlike poles of magnet attract each other. Okay. For example, if I take this as north pole and this as south pole, in the similar way this as north pole and this as south pole, what happens when I try to bring the like poles? If these two are the south poles now, right? So what happens when I take them near? Okay. So if these are the south poles, right? I am taking them near each other. What happens is they repel. Repel is nothing but reject. Okay. So during our childhood, we have always done this experiment with our magnets, right? Whenever we are playing with the magnets, what do? We try to connect them, right? If this is the south pole and this is the south pole, if we try to connect each other or attract each other, they repel. Okay. So like poles always repel each other and unlike poles, they always attract each other. Now, as I said, if this is a magnet, there is magnetic field around it. So what do you actually mean by that magnetic field? Okay. The definition is the imaginary lines representing magnetic field around a magnet are known as magnetic field. Okay. As you can see in the diagram, these are the magnetic lines. Okay. These are the magnetic lines. So the imaginary lines representing the magnetic field. As I said, if this is the magnet, these are the imaginary lines. Okay, this is the field, magnetic field, right? So these lines, imaginary lines which are showing the magnetic field are called as magnetic field lines. Okay. What are the properties of magnetic field lines? They can ask this question as well. Define magnetic field lines and what are the properties of magnetic field lines? Okay, this can be asked for 3 marks. So the properties are originate from north pole of a magnet and end at south pole. Okay. So magnetic field lines, they are originating from the north pole and they are ending at the south pole. Okay. Originating is nothing but initiation. They are coming out from the north pole and they are ending at the south pole. And inside the magnet again they are going from the south pole to the north pole. Okay. They originate from the north pole and end at the south pole. This is the first property. Are closed and continuous curves. As you can see, these are closed. Okay, this field line, if you see, they are totally closed. Inside the bar magnet, they are going from south to north and they are closing. They are closed curves. Okay. are crowded near the poles, and if these are the poles, okay, they are crowded, that is all the field lines, they have to meet at the south pole and the north pole. They are not intersecting, but they are meeting here in the south pole and the north pole. Okay, so they are crowded near the poles. These are the poles. This is the south pole and this is the north pole. So they are crowded at the poles. Never intersect each other. See, as you can see here, see, they are never intersecting. Intersecting is nothing but they are crossing over. Okay, they are not at all crossing. They are not at all cutting each other. Okay, see here, they are not at all intersecting. Okay, so never intersect each other. The direction of the magnetic field is indicated by the arrow of the lines at any point. See, the direction of the magnetic field. I had told you, right, like magnetic field has direction and magnitude. So this is the direction. The direction is shown by an arrow. These are the properties of the magnetic field line. So just by looking at the diagram or just by drawing the diagram, you will be able to explain all these properties. Okay, I hope you are clear with that. Magnetic field due to current carrying conductor. As I said, in a current carrying conductor, this is a conductor and we are passing current through it. Okay, we are applying some voltage and current is passing through this conductor. So this conductor will act as a magnet because it has magnetic field lines around it. Okay, so in the similar way we will be discussing about some conductors. Very first is straight conductor. If this is the straight conductor, okay, if this is the straight conductor and we are and the current is flowing through this, okay, this is the straight conductor and current is flowing through this. So what happens? How are the magnetic field lines? Okay, magnetic field is represented by concentric circles which become larger and larger as the distance increases. See here, this is the conductor and these are the concentric circles. This is nothing but the magnetic field. So near the conductor, the concentric circle, it is very small, but as the distance increases, the concentric circle becomes larger and larger, right? So they can ask this question as well, right? Magnetic field due to current carrying conductor. What are the three conductors, or how the magnetic field varies in different types of conductors? Okay, I just hope you are clear. Straight conductor, in straight conductor what happens? The magnetic field, it is represented by the concentric circles and the distance of the and as the distance increases, the concentric circle becomes larger. Okay, so the right hand thumb rule, it gives the direction of the magnetic field lines. Okay, the right hand thumb rule, it is for the straight conductor. So for the straight conductor, it gives the direction of magnetic field lines. As I said, this is the straight conductor, right? So it gives the direction. So whenever I am holding this in this way or in this way, okay, so let me explain in this way. So when I am holding this straight conductor in my right hand, okay, so this is how we are holding it. So this is the right hand thumb rule, okay, because I am using my thumb here. So right hand thumb rule, what does it say? It gives the direction of the magnetic field lines. Very first thing, it is to give the direction of the magnetic field lines. When you are holding a current carrying straight conductor in your right hand such that the thumb point towards the direction of the current. Okay, when I am holding this conductor in my right hand, so what happens is, and I am stretching my thumb over here. So thumb is showing the current. Okay, this is the direction of the current. This is the straight magnet and it happens only in the straight conductor. Okay, right hand thumb rule, it is applicable only for the straight conductor. You need to remember that. Okay, so when I am holding it like this, what happens? This thumb, it is showing the direction of the current. Okay, next, then your fingers will wrap around the conductor in the direction of the field lines of the magnetic field. So I am wrapping this conductor. Wrapping is nothing but holding this conductor. Okay, so my fingers, okay, these other four fingers, these are showing the magnetic field line. This is showing the direction of the magnetic field lines. Okay, so this is known as right hand thumb rule. I just hope you are clear with this. So here is here's the diagram as well. So this is the right hand, and what happens if this is the conductor, what happens? This is the current. Okay, the thumb is showing the direction of the current and the fingers are showing the magnetic field. See, the fingers are in this direction, that is why the magnetic field is in this direction. I hope you are clear with this right hand thumb rule. It is also important for your examination. Okay, so sometimes they may ask for what type of conductor is the right hand thumb rule applicable. Okay, for what type of conductor the right hand thumb rule is applicable? It is applicable only for the straight conductor. Okay, now we will study about the circular lip. What happens when a wire is made circular and current is flowing through it? See, this is nothing but a wire which is made circular, and here we are connecting the voltage so that the current passes through it. Okay, what happens in a circular loop? How are the magnetic field lines in a circular loop? Okay, the magnetic field lines of force near each segment of the wire are circular and form concentric circles. Okay, so at the end what happens? The magnetic field lines, they are circular. Okay, they are concentric in nature. These are also like concentric in nature. They have just shown you the arc of it, but those are concentric in circle. Okay, concentric in nature. Okay, so what happens at the end? What happens? These are concentric circles. The magnetic lines of force near the center of the coil are almost the straight lines. Okay, so as we go to the center of the coil, this is the center of the coil, right? So the magnetic field line, they become straight. Okay, what happens? The magnetic lines of force near each segment of the wire are circular and form concentric circles. So near the each segment, that is during this pole type region, what happens? Those are concentric in nature. Okay, they are circular in nature. But at the center, what happens? The magnetic lines of force near the center of the coil, they are almost straight lines. So at the center, they are almost the straight lines. Now in a solenoid. Okay, so what do you mean by solenoid? Solenoid is also a type of conductor. Okay, the long cylindrical coil consisting of large number of turns of an insulated copper wire is called as solenoid. So the long cylindrical coil, it is a coil consisting of large number of turns, that is the wire is wounded on it. Okay, so if this is the coil, if this is the conductor, the wire is wounded on it, right? So that is called as solenoid. So what are the type of magnetic field lines in this solenoid? The magnetic field around a current carrying solenoid is similar to the magnetic field produced by a bar magnet. I had shown in the bar magnet, right? What happens if this is the conductor? The magnetic field lines were circular in nature, right? And at the poles, they were crowded near the poles, right? In the same way, here in the solenoid, as you can see, they are concentrated here. Okay, they are circular in nature, and here the poles, if this is the pole area, these are crowded, totally crowded. Okay, so in the solenoid, the magnetic field lines are same as that in the bar magnet. The field lines in a solenoid are in the form of parallel straight lines. So here the field lines, they are parallel straight lines. Okay, so in the center, what they are parallel straight lines. Okay, in the conductor, if the magnetic field lines are passing through it from the regions, what happens in the conductor? They are totally parallel is nothing but one above the other. They are never intersecting each other, they are not touching each other. What they are parallel to each other. Okay, no, previous one. The field lines in a solenoid in the form of parallel straight lines. Okay, this indicates that the magnetic field is same at all points inside the solenoid. Okay, this shows how uniform the magnetic field is. Okay, so the magnetic field is similar, that it is same and uniform at all the points in the center. Okay, sometimes they will ask you like why are the magnetic field lines parallelly straight in a solenoid? Okay, so this is the answer. So magnetic field is same at all the points inside the solenoid. Okay, now let us study about the electric motor. So the definition of electric motor is nothing but an electric motor is a rotating device that converts the electrical energy to mechanical energy. Okay, electric motor, what does it do? It converts the electric energy into the mechanical energy. Electric energy is nothing but in a motor, what are we doing? We are giving an electrical supply. Okay, we are giving electric supply from the circuits. So the electric supply, it is converted into mechanical energy. When the electric supply is given to the motor, what happens? The shaft, it starts rotating. Okay, the rotor in the motor, it starts rotating. Okay, so the electric energy is converted into mechanical energy. So here is the diagram of electric motor. I don't think there's any necessity of explaining this, because in the exam they are only going to ask you the this diagram. Okay, they are not going to ask you any explanation of the diagram. They will just ask you the diagram. What is the draw a neat label diagram of electric motor? That's it. Okay, sometimes they may ask you the uses as well. So the uses are, they are used in electric fans, refrigerator, washing machines, computers, etc. So in almost all the appliances they use electric motors. Okay, so only the diagram is important. Sometimes they may ask you the uses as well. Okay, now electromagnet. A soft metal core made into a magnet by the passage of electric current through a coil surrounding it. Okay, what is the definition? A soft metal core. Okay, it is a soft metal core, soft iron core, okay, into a magnet by passage of electric current. So this, if this is the metal core, okay, if this is a soft metal core, when we are passing electric current through it, what happens is it is converted into an electromagnet. Okay, by passing the by passing the electric current into a soft metal core, we are converting that to a magnet, okay, through a coil surrounding it, and we also have a coil surrounding it. Okay, that is called as an electromagnet. What are the uses of this electromagnet? For heavy lifting loads in hospitals, in instruments. So these are the uses of electromagnets. Okay, I just hope you are clear what is electromagnet. If this is the coil or this is the conductor and we are passing current through it and the coil is surrounded to it, what happens is this this metal core, it will act as a magnet. Okay, so this magnet which is produced because of the electricity, it is made because of the electric current, right? So it is called as electromagnet. Okay, the uses are for heavy lifting loads in hospitals, in instruments and all. So these electromagnets are used. Electromagnetic induction. So this is also an important question, guys. So electromagnetic induction, they may ask you the definition for 1 mark. Okay, the phenomenon of producing electric current in a conductor by moving it perpendicular to the magnetic field or vice versa is called as electromagnetic induction. Okay, the phenomenon of producing, so producing the electric current by moving it perpendicular to the magnetic field lines. Okay, if these are the magnetic field lines, we are moving it perpendicular. Perpendicular is nothing but moving it 90 degrees. Okay, so that is called as electromagnetic induction. Okay, so the phenomenon of producing electric current in a conductor by moving it perpendicular to a magnetic field. So here we are not applying any kind of electricity. What we are doing, if this is the bar magnet and these are the magnetic field lines, what we are doing, we are placing a conductor perpendicular to the magnetic field lines. Okay, we are placing one conductor perpendicular to the magnetic field lines, that is we are cutting these magnetic field lines. So that phenomenon is called as electromagnetic induction. Okay, electric generator. Electric generator is an application of electromagnetic induction. Okay, so electric generator, it works on the principle of electromagnetic induction. Okay, electric generator is nothing but it is a device in which mechanical energy is converted into electrical energy. In motor, what happens? The electrical energy is converted into mechanical energy, but in generator, the mechanical energy is converted into electrical energy. Okay, generator. Okay, as the name indicates, generator, it generates electricity. Okay, electrical generator, what does it do? It generates electricity. So again here the diagram is very much important. Okay, they can ask you the diagram of electric generator as well. Okay, you will have to label it accordingly. So the labeling is also very clear, you can just note it down or it's present in your textbook. Okay, AC generators produce AC. Okay, so AC generator, alternating current. AC is nothing but alternating current. So AC generators, they produce alternating current. Okay, so alternating current is nothing but a current which periodically changes its direction. So AC is nothing but it is periodic, it is sinusoidal. Okay, periodically it is changing its direction. Direct current generators produce DC. Okay, so DC generators produce DC. DC is nothing but direct current. Here there is no periodical change. In alternating current, it is alternating, right? It is sinusoidal in nature. But in direct current, it is not alternating. It is same. Okay, a current which does not change its direction. Okay, the current which does not change its direction. A direct current, it is always straight. Okay. It will never change its direction, its direction is always the same. So Fleming's right hand rule. So this Fleming's right hand rule, it gives the direction, okay, direction of the electric generator. It gives the direction of induced current. Okay, in electromagnetic induction, what happened is we were inducing the current, right? So the direction of this induced current is given by Fleming's right hand rule. Okay, this is the right hand rule. So the figure is given. Stretch the thumb, forefinger and middle finger. We are stretching the thumb, forefinger and the middle finger of right hand so that they are perpendicular to each other. See, they are at 90 degrees to each other, right? They are at 90 degrees to each other. They are perpendicular to each other. If the forefinger indicates the direction of the magnetic field, if the forefinger it indicates the direction of the magnetic field and the thumb shows the direction of motion of conductor, the thumb shows the direction of motion of conductor and the middle finger will show the direction of the induced current. So the middle finger will show the direction of induced current. Okay, this rule is called as Fleming's right hand rule. So just by looking at this picture you can explain it. Here they have shown, see, motion, and this is the field and this is the induced current. This is the motion of the conductor, this is the magnetic field and this is the induced current in a conductor. Okay, I just hope you are clear with this. They can ask the Fleming's right hand rule as well for 2 marks. And what direction is it giving? It is giving the direction of the induced current. Okay. So now we are at the last part of this chapter. So what precautions should be taken to avoid the overloading of domestic electrical circuits? Overloading is nothing but what happens when we are using many appliances at the same time. For example, washing machine, microwave, mixer grinder, refrigerator. What happens if we are turning on all these appliances at the same time? So it causes overloading. Okay, overloading is nothing but applying more load, more than the constant rating. Okay, more than the required rating. What we are doing, we are applying the load. That load is called as overloading. So what happens? What are the precautions to take so that we should prevent the overloading? Okay, the circuit should be of proper current rating and appliances should be connected accordingly. So the circuits whichever are made in our commercial places or at home, so what happens is the circuit should have current rating. Okay, and we need to use that appliance at that current rating. Okay, so if this is a place where we are using the mixer grinder, we need to use the mixer grinder itself. Okay, if that is the board which is designed to use the mixer grinder, we need to use only mixer grinder over there. We can't use any washing machine or refrigerator over there. Okay, we need to use the appliances such that the current rating is given to that circuit. Okay. Wires should be checked from time to time and those wires whose insulation is worn should be immediately repaired. Okay, we need to always check the wire time to time. If at all the insulation is worn out, that is if at all the insulation, the upper part, that is the plastic part of the plastic or the rubber part of the wire is removed, we need to repair it as soon as possible. Okay. Connection of too many appliances in a single socket must be avoided. So if there is a socket and there are so many sockets present in that electric circuit, what happens is we use all those socket. Okay, we should not use all those socket simultaneously. Okay, at the same time we cannot use all the sockets. We need to just use it alternatively. Okay. Electric fuse. So electric fuse, it is used for the safety purpose. It is a safety device. Okay, so to prevent the overloading or overcurrent, we need to use this electric fuse. It is the most important safety device used for protecting the circuits due to short circuiting or overloading of the circuits. So it is a safety device which is used to protect the circuit. Okay, to protect the other circuits which are present in our home, we need to use this electric circuit because it protects the all other circuits from overloading and overcurrent. Okay, so with this I wind up this chapter. If at all you have any doubts, you can let me know in the comment section. I just hope you are clear with all the topics. If at all you are not clear, please let me know, and thank you for watching guys. All the best.